In this video, I am going to demonstrate how to graph polar curves in Desmos. So I have uploaded this particular Desmos spreadsheet into More, so you should have access to it. And the first thing that you should notice is that it's going to look like this. Tracing polar graphs will show up here. And in order to actually get the graphs, just click on the little triangle, and you will have these polar curves showing up. So I'm going to demonstrate exactly what this does and how it works, and then we can take a look at some other curves and how you can play around with these to help you when you're doing some calculus with polar curves. So first of all, if we just click right here, you're going to get this graph of a rose curve, which is the curve r equals 2 plus 7 cosine of 3 theta. And so all you need to do is just click on that on or off, and the graph will show up. Then we have, if I turn that off and I turn this on right down here, you'll notice nothing happens. But then when I click on this little arrow right here, you're going to get the rose curve being traced out in real time. And so it's actually tracing out from theta 0 to theta equals 2 pi. And it's programmed so that this will just keep going over and over and over again. Now we can put in any rose curve and we can have it trace out like this. Now what's really fun is when we combine these two graphs. So if I turn that off, I turn this one back on, and then I turn this one on, and I start the tracing from the beginning. This is what we see. We can see how the red curve is tracing over the dashed curve. And once again, it will continue to do this over and over again. So, as I already mentioned, this is a rose curve. And what I want to do now is take a look at some simpler curves. So let's just go back to the function on top, and let's just put in something a little more simple. So I'm just going to take that out, and I'm just going to put in r is equal to 3. And so when we put in r is equal to 3, that is a very, very simple polar curve. That means this is the curve where the radius is 3. Doesn't matter what the angle is, but the radius is always going to be equal to 3. And it's simply a circle, right? And I could do that for this. I'm going to be careful not to interfere with this, what's in the parentheses, which is the interval. That's what's helping it to graph. So I'm simply going to put 3 in here as well, and click on that. And now we can see it trace out from 0 to 2 pi. This is a little bit easier to see that we're going from 0 to 2 pi. Starting at 0, pi over 2, pi, 3 pi over 2, and finally over to 2 pi. All right, let's be a little more creative. Let's stop that. And let's do, how about 3 sine of theta? Whoops, theta. And let's type in 3 sine of theta here. And so we also recognize this as being a circle. Whenever you have sine of theta, it's going to be centered around the y-axis. If I was to make this a negative, it would simply be below the x-axis. If it's positive, it's above the x-axis. And you'll also notice that the diameter of this circle is 3, which is this number here. So if I change the 3 to a 5, the diameter of the circle would be 5. Not the radius, but the diameter would be equal to 5. And again, if I was to make that a negative, it would be down there below. And so if I change both of these functions, negative 5 sine of theta, and now I can trace this out from 0 to 2 pi. Now notice it's going around to 2 pi. It goes in a distance of 2 pi, it actually goes around twice. And of course, you could graph these by making a table of values. These are fairly simple graphs that you should be able to make a table of values to kind of help you understand a little bit as to why these graphs look this way. It all comes from just making a table of values, but that gets to be very tedious when we get into more difficult types of equations. All right, what if we were to change this from sine to cosine? And change both of them to cosine. So we're going to get a graph that looks like this. And it's a -5. If I change it to a +5, it flips over to the other side of the y-axis. And of course, we can trace this out as well. Now, the tracing is just fun to watch. It can be useful when you're trying to identify the boundaries of your integration. But for now, let's just take a look at some different curves with the dashed line. What happens if we add something to this? If I do 2 plus, all right, now we have a limacon. This is a typical limacon. You have a limacon because the 5 is greater than the 2. If I was to make the 2 something greater, that's a little bit big, so let's just make that 2 into a 5 and make the coefficient of the cosine 2. We have a cardioid. Right? That is a flattened circle, which we call a cardioid. And if I was to make this a slightly bigger number, 4.5, you can see how the bigger the coefficient of the cosine becomes, the more this gets pulled inward here. And if I was to create that same here, 4.5, we can now trace that out. Oops. And we're tracing it out from 0 to 2 pi. So that is a cardioid. And once again, if we take this number that is all by itself, and if it is smaller than the coefficient of the cosine, then it becomes a limacon. The limacon is when you have the inner loop. All right, that is the inner loop. So we have cardioids, we have limacons. The first one that we looked at was a rose curve. If I wanted to turn this into a rose curve, all I would need to do is have some other type of an angle, 3 theta or 2 theta. If you have 2 theta, you have 4 leaves on your rose curve. If I have 3 theta, I have 6 rose petals or leaves, 3 inner ones and 3 outer ones. If I was to do 5, I actually have 10 petals. So the number of petals is always going to be double what the coefficient of the angle is going to be. And again, I don't expect people to memorize all of these things. You don't need to be able to graph these by hand, but you should be able to graph these in Desmos and have a good understanding of what you're looking at and why you're looking at that. One other thing that we can do is, let's see if I change it to 12. Oh yes, make that a big number, and now we get looks like a starfish. And that's because this number out here is bigger than this number. If I change that 5 to a 15, so the graph changes drastically whenever you change any of these numbers. So changing any of these numbers even a little bit can change the way they look. If I put a 2 in there, if I put a 5 in there, what if I get rid of this and just put in a 1? So it's fun to just play around with these and see how changing these numbers will affect the look of the curve. What if I change this to a minus sign? Okay, it's going to rotate it pretty much. Go back to a plus sign. And let's make this 1 into a 16. Let's make the 5 into a 25. So we have rose curves, limacons, cardioids, circles. And of course, we can also, if we wanted to, let's make this theta equals, let's do pi divided by 2. Oh, it doesn't like that. Okay, I guess it won't do theta divided by, I thought it would. So we'll just stick with in terms of r. R equals 4 cosine theta. There we go. So now we have a circle. All right, one last thing that you can do is you can change the interval over which it is graphing. Okay, so you can change these intervals. If you want, just type in pi. It'll put in pi there. You can type in pi and then divide it by 2. And let's say we want this to go from 0 to pi over 2. Change this one from 0 to pi over 2. And so up here in this is really the interval that's telling us what it's going to trace out here, because theta is greater than or equal to 0 but less than or equal to a, and with the slider here, a is constantly changing. So let's just take a look at that. What I have to do down here is change this from 0 to pi divided by 2, and now the slider itself will only go from 0 to pi over 2. So let's see how far this graphs. 0 going up to pi over 2, boom, it's done. So you can see it's only graphing, and what are we graphing? We're graphing a rose curve. Let me put in this function here. And so it's only graphing from 0 to pi over 2. It's tracing it out from 0 to pi over 2. So you can play around with the bounds, and you can play around with the different graphs, and all of these will kind of give you an idea as to what these various types of polar curves look like. So in the next section, when you're actually finding the area under a polar curve, it's helpful to graph it and maybe trace out where you are graphing. So as an example, let's say we want to do 2 plus, and we want to go from 0 to, let's say we only want to know, we want to find the area under this curve between 0 and pi. All right, and so let's put the same function in both of these. And I'm going to change this to pi, make sure all my bounds are in agreement here, just so I don't get something weird. All right, so first of all, just taking a look at this. This is what the graph of the polar curve is going to look like when it traces out from 0 to pi. And so when we're finding the area underneath the polar curve, we're finding the area between the pole, right, at 0, 0, and the curve. So we're finding all the area underneath that, all the way around to pi. If you want to see what it looks like when you trace it out, you can just put the other curve on. And so we have a graph that looks like that. All right, well, that's pretty much it for this video. This is just kind of to get you started on looking at polar curves, so that when we start doing a little bit of calculus with polar curves, you'll have the means of graphing them and knowing what it is that you are looking at. All right,